Now let's look at how carbon dioxide is transported in the blood. It says carbon dioxide is transported in the blood in three forms, and here we're looking at a blood capillary and the tissue cells. So, dissolved in plasma, 7 to 10%. So there's carbon dioxide just entering the plasma, dissolving in the plasma, so just a small amount of carbon dioxide travels in that fashion. Chemically bound to hemoglobin, just over 20%. We know a lot of oxygen is carried on hemoglobin, but just over 20% of carbon dioxide is bound to hemoglobin. So let's look at that arrow. There's our 20% arrow. Enters the blood, enters our red blood cell, so there's carbon dioxide binding with hemoglobin, creating that complex. But as bicarbonate ions, there's a bicarbonate, it's a negatively charged ion here, in plasma about 70%. So this is how carbon dioxide is transported the most, 70% of it, and it's not in our red blood cells, it's in the plasma, but it's not the dissolved carbon dioxide. So here's our large arrow. It actually does enter the red blood cell initially. We have carbon dioxide. It reacts with oxygen, and we produce something called carbonic acid. And carbonic acid will then dissociate into the bicarbonate ion and a hydrogen ion. Now the bicarbonate ion will leave the red blood cell, and since a negative is leaving, a negative will come in to balance the charges. And we call that the chloride shift. We have this chloride ion being swapped for the bicarbonate ion. So there's bicarbonate in the blood. Doesn't have to enter the red blood cell. We can see carbon dioxide will react with water in the plasma to produce that carbonic acid and then split into its hydrogen ion, and which increases acidity, and bicarbonate ions. So we have bicarbonate ions either being created in the plasma, it's a slow process, versus in the red blood cell, which is a fast process because there's an enzyme, carbonic anhydrase, but the end result is 70% of carbon dioxide travels in the blood in the form of the bicarbonate ion because it reacted with water and then split into its anion and cation. Now once we get to the lungs, here's an alveoli or an alveolus singular, we need to breathe out this carbon dioxide, eliminate it, but most of it is in the form of the bicarbonate ion, so we need to reverse back to carbon dioxide. Well, not the dissolved carbon dioxide in plasma, that can just diffuse into the alveolus, but the bicarbonate ion, whether we went the slow route or the fast route, just goes in reverse order. The bicarbonate ion will join up with a hydrogen ion to make carbonic acid and then break up into its parts, carbon dioxide and water. Water will remain in the plasma, carbon dioxide will leave. That's the slow method in the plasma. Of course, we have our enzyme in the red blood cells where bicarbonate ion will join up with its hydrogen ion to form carbonic acid and then quickly get converted to carbon dioxide and water, with the carbon dioxide diffusing into the alveolus so it can be eliminated. So the Haldane effect states that the amount of carbon dioxide transported is affected by blood oxygenation. This encourages that carbon dioxide exchange at the tissues and at the lungs. So at the tissues, we saw that as more carbon dioxide enters the blood, more oxygen dissociates from hemoglobin, the Bohr effect, right? So that the oxygen can leave the hemoglobin and enter our tissues where it's needed. As hemoglobin bound to oxygen releases the oxygen, it readily binds to carbon dioxide, and there's our carbon dioxide hemoglobin complex, carbaminohemoglobin. That's the Haldane effect. So in the lungs, rise in oxygen encourages hemoglobin to release carbon dioxide. So the opposite at the lungs and at the tissue, of course, because we need the opposite exchange of gases. So this will explain how breathing will affect the acid-base balance in the body, because changes in our respiratory rate and the depth of our breathing will affect pH. And this is how, when you breathe slowly and shallow, that increases carbon dioxide in the blood. Carbon dioxide in the blood will drop the pH, because we saw how carbon dioxide binds with water and then separates from the carbonic acid to the bicarbonate ion and hydrogen ion. And the hydrogen ion is what increases acidity. Increased acid is a lower pH. Opposite, rapid deep breathing decreases carbon dioxide, and that will raise pH, because carbon dioxide will bind, or the bicarbonate ion will bind with the H plus and remove it from solution, making it less acidic, therefore raising the pH. So changes in your breathing rate and depth help adjust pH, because pH has to be kept within homeostasis in the blood, slightly basic, 7.35 to 7.45, and the breathing rate helps with our adjustment of blood pH. So breathing plays a major role in acid-base balance in our body. So I'll end this video with hypoxia, which is a term we've seen in previous chapters. That's inadequate oxygen to the tissues. It can result in cyanosis, it's bluing of the tissue. So there's a lot of different types of hypoxia. Some we've seen, like anemic hypoxia, where there's not enough red blood cells to carry oxygen. Ischemic hypoxia, when there's a blockage in circulation. But we also have something called histotoxic hypoxia. Cells are unable to use the oxygen, like in poisoning. There's hypoxemic hypoxia, reduced arterial oxygen, abnormal ventilation, pulmonary disease, low levels of oxygen in the air. That's another type of hypoxia. And carbon monoxide poisoning is a type of hypoxia, because hemoglobin will bind readily to carbon monoxide. Carbon monoxide just has a extremely high affinity for hemoglobin, much greater than oxygen. So carbon monoxide will take the place of oxygen on the hemoglobin, which of course is not a good thing.